Chapter 2, Section 7, Graphing Techniques. So I've determined that I'm going to do this section again as a disembodied voice, mainly because due to the graphing and showing these different techniques, it's a little bit easier to do it with an electronic setup, so using a web-based graphing program. That way you can see the graphs, you can see how they transition, and not have to deal with me trying to draw a grid on the board and make it work through that way. If this was an in-class situation where we were in person, I actually take advantage of technology and I'll have it projecting onto the whiteboard. And so it will graph a grid. And then I can demonstrate how these techniques work and then have it overlay that with the actual graph. And it works quite nicely. Not as easy to do that when doing these recordings because I don't have the ability to project that grid and do all that. So we're just going to do it as a disembodied voice, and we're going to deal with these different graphing techniques. We're not going to get too advanced into this today. We're just going to get into some basic methods and some things that come from those methods. So our first thing is vertical stretching or shrinking of the graph of a function. So that means you're actually taking the graph and just stretching it out vertically or shrinking it vertically. So you're making it taller or you're making it shorter, or in relation to itself, it's taller or shorter. So suppose that a is greater than 0. If a point xy lies on the graph of f of x, then the point xay lies on the graph of y equals a f of x. So basically what this is saying is that if you take a function and multiply it by some constant, that your y value, or every point on your graph, the y value is going to be multiplied by that constant. So if y would have been 2 for f of x, and a is equal to 3, then y would now become 3 times 2, or 6. And we'll demonstrate that in just a moment. If a is greater than 1, then the graph of y equals a f of x is a vertical stretching of the graph of y equals f of x. So if a is greater than 1, then you're multiplying by a number greater than 1, and therefore you are stretching the graph vertically. You're making it bigger. If a is between 0 and 1, then the graph of y equals a f of x is a vertical shrinking of the graph of y equals f of x. So you're multiplying it by a number less than 1, greater than 0, so a positive number less than 1, and therefore you're going to be shrinking the graph or making it smaller in the vertical direction. Now, something to take note of is that the x-intercepts of the graph will remain the same, because remember, we're multiplying by the whole thing by some value, which means when when y is equal to 0, multiplying by any number is still going to give us 0. So the x-intercepts remain the same, but the y-intercepts are going to be affected. Because wherever it crosses that y-axis, that's now going to be multiplied by a. So let's pop over to one of my favorite graphing programs, which is Desmos.com, or I should say graphing calculators on the web, Desmos.com. So let's see what we're talking about here. So if I make f of x equal to x squared. So we see this function that f of x is equal to x squared. Now, what this is telling us is if I were to modify that function and multiply it by some constant. So I'm just going to say, I'm just going to put y in instead of f of x at this point because I don't want to confuse saying f of x in this. So y is equal to, let's go for the 3 like I said originally, 3 times x squared. Now, if we look at this, we'll notice that when x was equal to 1, originally y was equal to 1. But now when x is equal to 1, y is equal to 3. And I'm just going to switch this into a slightly different mode here. Well, I would, but they changed it on me. There we go. Now they call it big A or little a. They used to call it projector mode. So we can see the grids a little better here, but we can see that when y was equal to 1, now it's equal to 3. When y was equal to 2, here, now it's equal to 6. So it just stretched it out. I know it can be a little confusing when you first look at this because you could also say, well, wait a second, didn't that just squeeze it horizontally? And you could say effectively, yes, you did, but what we did to it was we stretched it vertically. It just has a similar effect to what happens if we were to shrink it horizontally. But you can see how that works. Now, coming back to the slides, let's see what happens with horizontal stretching or shrinking of the graph of a function. So horizontal stretching or shrinking, now we're changing it lengthwise as opposed to height. Suppose that a is greater than 0. If a point xy lies on the graph of f of x, then the point x over a y lies on the graph of y equals f of a times x. So we see that this is causing a division to happen. When we take this number, we're taking x and dividing it by that value. If a is greater than 1, then the graph of y equals f of ax is a horizontal shrinking of the graph of y is equal to f of x. Now that may be counterintuitive, but remember I pointed out that we're dividing x by a. If you think about what's happening, if you multiply your input by some value greater than 1, then really what you're doing is you're telling the function you're further along the x-axis than you really are. X is 2, but if a is 3, now you're saying x is 2, but give me the function value, or if x was 6, 2 times 3. So it's actually getting to things faster, so that's why it's a horizontal shrinking. If 0 less than a less than 1, so a positive number less than 1, then the graph of y equal to f of a times x is a horizontal stretching of the graph of y equals f of x. So if you multiply x by a number less than 1, then what's happening is it's taking longer to get to the certain outputs. So that's actually stretching out your graph as opposed to shrinking your graph. And with this one, again, note that the y-intercepts of the graph remain the same, but the x-intercepts are affected. So now we're multiplying x by some value and getting to those y values. So the x-intercepts are going to be affected, but the y-intercepts of the graph are going to remain the same, because when x is equal to 0, it doesn't matter what value of a you multiply it by, it's still going to be there, so it's not going to change your output on the function. So going back to Desmos.com, I'm going to modify this a little bit and say, well, this was the vertical stretch. Now what I'm going to do is I'm going to put that in parentheses. And we see that we now have we actually have a horizontal shrink, where x was equal to 1, now it's equal to 1/3 of that. If I go out to where x was equal to 3, which is all the way up here, now we see that it's doing the same thing that it did originally. It does that same thing at x equal to 1. So it's actually shrinking it down. But you saw how it looks like a similar thing. We squished it. But in this case, we squished it by telling it to operate further along the function than x is really. Whereas previously, we made it taller by telling it to multiply the output by a certain value. Now, one thing I want to point out with that is the difference between these. If you remember with the vertical stretching or shrinking, I'll get back there to that, we took the output of the function and multiplied it by some value. So you affect your vertical when you do something to the output of the function. So here we take f of x and we multiply it by some value. So we're taking the output and multiplying by it. That affects the vertical. Whereas when we take the input x and modify it, so in this case multiplying it by a value, we affect the horizontal. So very important for us to keep that in mind. Continue on, reflecting across an axis. Now, if you remember with the vertical and horizontal stretching and shrinking, we always had those values greater than 0. We gave you from greater than 1, and we had between 0 and 1, but we didn't allow it to go negative. And that's because when you go negative, you are reflecting across an axis. So the graph of y equal to negative f of x is the same as the graph of y equal f of x reflected across the x-axis. If a point xy lies on the graph of y equal f of x, then x negative y lies on this reflection. So again, notice that we have f of x that we're then negating. So that means whatever our output would have been, whatever y would have been, now we're going to negate it. So that flips it across the x-axis. If the output would have been 4, now it becomes negative 4. If the output would have been negative 7, now it becomes positive 7. So it reflects it across the x-axis. And notice that still is a vertical change. We're flipping it vertically. The graph of y equals f of negative x is the same as the graph of y equals f of x reflected across the y-axis. If a point xy lies on the graph of y equals f of x, then negative xy lies on this reflection. So now if you look at that, we're negating the input. And so that's affecting it horizontally. Now what we're saying is, when I have x, give me what would have been the results of the negative value of that. So if I plug in 4, it's going to give me the result that the function normally would have given for negative 4. So that's flipping it horizontally over the y-axis. Now this leads to another thought of things of symmetry with respect to axes or the origin. Because if we think of some of our graphs that we deal with, they kind of look like a mirror image. If you look at the x-axis or the y-axis, you see, gee, if I were to just put a mirror there, I would still see the same thing. So the graph of an equation is symmetric with respect to the y-axis if the replacement of x with negative x results with an equivalent equation. So again, this is a horizontal thing. It's symmetric with respect to the y-axis, which is a vertical line. So that means whatever happens on the right side of that x-axis, the y-axis, happens also on the left side. So if we can replace x in the equation with negative x and get the same equation back, we're symmetric with respect to the y-axis. The graph equation is symmetric with respect to the x-axis if the replacement of y with negative y results in the equivalent equation. So now if we take the output and then negate it and we get the same graph, then it's symmetric with respect to the y-axis. Again, that's a vertical thing. We've got mirroring vertically. And then the graph equation is symmetric with respect to the origin if the replacement of both x with negative x and y with negative y at the same time results in an equivalent equation. Okay, so we're going to try to demonstrate these. So basically that means if you negate the input, it also negates the output. And then it looks the same. So let's go back to Desmos and take a look at these. So I'm going to get rid of the second part here and go, well, we've got this f of x is equal to x squared. Well, if I negate the input of this, what happens? So if I go negative x squared, I get the exact same thing. Turn it off, turn it on, turn it off, turn it on, right? I get the same thing. So I plugged in negative x in place of x, and I got the same output. So x squared is symmetric with respect to the y-axis. Let's change to a different function here. I'm going to get rid of that one for a second too. I'm going to cheat and go here. Oh, it's not going to let me do that. I thought it would let me get rid of that, so I can do it here. In fact, I'm going to change it. I'm going to say x equal to y squared. There we go. Get that out of the way. So now we see that I have x equal to y squared, and we can just visually look at that and go, gee, that looks like that's symmetric with respect to the x-axis. But to verify that, we plug in the negative value for y. So I'm going to make this x, and I'm going to make this negative y. And if that's the case, then when I do this, it looks the same. So we can see that x equal to y squared is symmetric with respect to the x-axis. It reflects over the x-axis. I'm going to change this back to y equal to x, but now I'm going to make it cubed. So y is equal to x cubed. We can see that this obviously is not symmetric with respect to the y-axis. It's not symmetric with respect to the x-axis. But now I'm going to look and say, well, what happens if I go y equals negative x cubed? And we see, well, that didn't come out the same, but we didn't expect that to, right? Because plugging in negative x would have shown us that it was symmetric with respect to the y-axis. But what if I do this? Negative y is equal to negative x cubed. Remember, when it's symmetric with respect to the origin, replacing x with negative x makes the result turn into negative y. So the function x cubed is symmetric with respect to the origin. So we've got symmetric with respect to the y-axis, symmetric with respect to the x-axis, and symmetric with respect to the origin. And you can do this not only by graphing it, but you can just plug in the values and see what happens. Meaning, if I take x squared and I replace x with negative x, negative x squared becomes x squared. So that must be symmetric with respect to the y-axis. It came out with the same function. If I take x equals y squared, and I plug in negative y in place of y, negative y squared is just y squared, and therefore we come up with the same equation. It's symmetric with respect to the x-axis. Whereas if we take x cubed and replace x with negative x, then we end up with negative x times negative x times negative x, which we can turn into negative x cubed. And therefore, changing the input to the negative changes the output to the negative. And so you can do this just by plugging in negative x or plugging in negative y. Most often we deal with symmetric with respect to the y-axis and symmetric with respect to the origin, mainly because obviously if we have symmetric with respect to the x-axis, we don't have a function. Because if it reflects over the x-axis, it fails the vertical line test. So we generally deal with symmetry with respect to the y-axis and symmetry with respect to the origin, because if we're dealing with functions, it eliminates symmetry with respect to the x-axis. And that leads us into odd and even functions. A function f is an even function if f of negative x is equal to f of x for all x in the domain of f. Its graph is symmetric with respect to the y-axis. So just as I was saying, we're talking about functions now. If I can substitute negative x into the function and I get the same function back, then the function is an even function. And if you remember when I demonstrated x squared as a basic function, I also pointed out that the higher order even powers, x to the fourth, x to the sixth, x to the eighth, that they followed the same method, that they look very similar. It's just a flattening near the bottom or near the vertex, and the sides just got steeper. Notice x squared, that's x to the 2, x to the fourth, x to the sixth. Those are even powers. Those functions are even functions. You plug the negative x in instead of x, you get the same result. A function is an odd function if f to the negative x yields negative f of x. So basically, if you replace x with negative x, your result will be negative y. For all x in the domain of f, its graph is symmetric with respect to the origin. And that's what we just saw. Notice that was on x cubed. And when I talked about the basic functions, I said x cubed, x to the fifth, x to the seventh, x to the ninth, etc. The odd power functions, they had a similar look, except a flattening in the middle and making the sides steeper. So the same idea. So we see that if we can do that. So we can do that algebraically, plugging it in. And if we can turn the function back into the original function, then it's by plugging in negative x, then we have an even function. If we plug in negative x and we get the negation of the function, then we have an odd function. So a really handy thing to be able to do. Now, let's go into vertical translations. So we've dealt with stretching and shrinking. We've looked at whether they're symmetric with respect to the y-axis, symmetric with respect to the x-axis, symmetric with respect to the origin, whether a function is odd or even. Now we're going to look at vertical translations, which just means shifting the graph up or down by some amount. If a function g is defined by g of x is equal to f of x plus c, where c is a real number, then for every point xy on the graph of f, there will be a corresponding point xy y plus c on the graph of G. So what it's saying is, if you add c to the output of the graph, or of the function, then you're going to shift that function up by c, assuming that c is a positive number. If c is a negative number, you're going to shift it down. But that's all it's saying. So we're affecting the output. We have f of x plus c. So it's moving the graph up or down. A positive value, adding a positive value will move the graph up by that amount. Having a negative value will move the graph down by that amount. The graph of G will be the same as the graph of f, but translated c units up if c is positive or c units down if c is negative. The graph of G is called the vertical translation of the graph of f. So let's go back to Desmos and see this in action. Okay, well, we can do that pretty simply here. Let's get rid of that and that. And we can see, so we've got original graph is y equals x cubed. If I make that x cubed plus 2, then what this will do is it will move the graph up by 2. And that's exactly what it did. So it's just going to shift the graph up. So remember, you're dealing with the output. You already did the function x cubed. And then after that, you added on some value. And notice if I subtract some value, it minus instead of equals, there we go. If I subtract some value, then it's going to go down by that amount because you're affecting the output. You're finding the output of the function, and then you're adding something to it or subtracting something from it. So that's vertical translations. Horizontal translations, similar idea. If a function g is defined by g of x is equal to f of x minus c, where c is a real number, then for every point x, y on the graph of f, there will be a corresponding point x plus c, y on the graph of G. Now notice two things with this. One, they have you subtracting c from x. So we're affecting the input, right? We're taking the input x and we're subtracting some value from it. And what that's doing is that's moving the graph to the right or to the left by that amount. If c is with the f of x minus c, the graph is going to move to the right if c is positive, and to the left if c is negative. Now I point this out because another way that you look at it is just that f of x, the graph, will move right or left the opposite direction of the sign. So if we have f of x minus c, so if we had f of x minus 3, for example, it would move to the right 3 because it's minus 3. If we have f of x plus 3, it would move to the left 3, which is kind of the opposite of what you would expect. You expect if you go plus c, that it's going to plus some positive value, that it's going to move you to the right, but it's not. And it's for the same reason that with horizontal stretching and shrinking, when you multiplied by a number greater than 1, it actually shrunk it down because it got there faster. The same thing here, if you add a positive number to the input, so x plus 3, you're basically telling the graph or the function, act as if I'm 3 further to the right than I really am. So it shifts the graph to the left, compensating for that. The graph of G will be the same as the graph of f, but translated c units to the right if c is positive, or c units to the left if c is negative. The graph of G is called the horizontal translation of the graph of f. Again, this is done on the premise of f of x minus c. So let's go back to Desmos and take a look at this. And we can just stick with the same functions we've been using here. So y equals x cubed. So if I shift x and go x minus 4, get this out of the way, cubed, then since it's x minus 4, remember it said f of x minus c, so that says we should shift to the right by 4. So I expect my, I'll call it my x-intercept, it's my x and my y-intercept, but that's going to change when I do this. If my x-intercept is currently the origin, I now expect that to shift over to x equal to 4. And it does. So it goes the opposite direction of what the sign would imply. And that's why it's explained as x minus c does a shift to the right. So just keep that in mind. When you're dealing with something affecting the output, adding or subtracting a value is going to move it up and down respectively. If you're dealing with something where you're modifying the input, adding or subtracting is going to send it the wrong direction. It's going to send it left or right respectively. So back to the horizontal translation. So we have these things that we can put together, and we can actually do multiple at the same time. So let's do that. I'm gonna get back off of this, and I'm gonna put us into Desmos, and we're gonna try a combination on here. So we've done a lot with x cubed. Let's go back to x squared as one of our possibilities. So we've got x squared, but I'm going to actually go beyond that. What if we have 3, actually I'm going to make it negative 3. Negative 3 x squared plus 4. So negative 3 x squared plus 4. Now, what is that really going to do? Well, let's work through this and see. Our base function is x squared. So this is where we're starting. We are then going to multiply it by 3. So I'm going to come into a new one here, multiply it by 3. That should give us a vertical stretch. So where y was previously equal to 1, it'll now be equal to 3. So y equal to 3x squared. And we see that where y was equal to 1, it's now equal to 3. Now let's put that negative into effect, because what's that negative going to do? That's going to reflect it over the x-axis. Anytime we had anything that was a positive value is now going, for the output, it's going to become a negative value. So y equal to negative 3x squared. So we see now it just reflected it over the x-axis. And the last thing is we've got this plus 4, which is affecting the output. So that's going to be a vertical shift up. And that's where we can just do this. And we see that we have that vertical shift up. So we can work through this a piece at a time. And it's really cool when we do this on a whiteboard with a grid projected on it, because usually what I'll do is I'll take Desmos and I'll project its grid on there. And then we can actually draw on the whiteboard each of these points and say, oh, this is now going to be this, and this is now going to be that, just looking at these pieces of the equation, these graphing techniques. And we can watch the transition happen because we plot some points and say, well, it should be this. And then we let Desmos show us that next step, and boom, it does. It goes right over those points. So it's a really nice way to be able to do it. I'm sorry that you miss out on that by watching this in video format, because it's not quite as easy to do it that way. So that finishes graphing techniques.